So thank you very much, Lorenzo. So it's a real pleasure to be here. It's also a rare occasion, like because my parents-in-law actually they live 2 kilometers from here, so I could even walk to work today. I was going a little up, but so I want to tell you about radon transform, the connection to neural networks and splines. But actually, for those who know me, this is sort of my obsession is splines. So maybe that's more the talk I want to give you. So this slide here, in some sense, is a summary of my scientific career, because I've been very much spline focused, and then kind of uncovering a connection with all kinds of things like wavelets, approximation theory, regularization theory, and of course now the focus is on machine learning, and then I think there's a very strong connection between splines and machine learning, and that's what I'd like to develop today. So my talk will be a little mathematical, but I gather there are lots of mathematicians in your group, and so there's a nice connection between splines and operators, and usually you can associate, sorry for the click, so they're usually given a certain linear operator L, differential operator, you can associate a spline. So the operator will go from one space that I call X to Y, but what's important is this space X. Here's a superset of the space of test functions, and also the output space is a subset of the space of tempered distributions. And so then the operator needs to have some property. In some sense, it needs to be quasi-invertible. But we also like it to be linear shift invariant so that it would correspond to a convolution. And now the non-completely trivial part here is that we want the operator, we allow it to have a null space, but the null space should be finite dimensional. And then actually there needs to be a way to invert the operator, and that goes through the Green's function. So there must exist a Green's function that is a function that if you apply the operator to it, you get Dirac. And examples of admissible operators, so the derivative, the nth order derivative, so there the Green's function are the one-sided power functions. So this x plus to the power n minus 1 divided by the factorial. Now if you take the n here to be 2, you get the ReLU. And so the null space here is a space of polynomials. Now once you have such an operator, how do you define the spline? Actually, the spline is a function so that is defined on domain RD. And we will say it's a non-uniform L spline if the following happens. So if you apply the operator to the function, and then something curious happens because you just have a linear combination of Dirac impulses. And so we call that the innovation. And so to make it concrete, think of a piecewise constant function like here. And now if I apply the derivative operator in the sense of distribution, so I will get 0 almost everywhere except at the jumps where I get some Diracs. And so I get here 2 Diracs that will give me actually the location, the knots of the splines. And so that means that in some sense, even so, splines are functions that live in the continuums. They're intrinsically sparse because if you apply the operator at the end, they are specified by some discontinuities, which are this position of the knots, and then the strengths of the singularities. Now, once you have this definition of splines, in fact, what we like to do is work the other way around. Okay, so now you will take what I call an innovation, and so that could even be random. So you put like random Diracs with some random weights. And then, given that innovation, now you want to generate the spline that goes with it. And in fact, here the trick is just that you have the Green's functions. Like in physics, it's the way of solving the differential equation. And essentially here, what you will do is every time there's a Dirac, you just replace by the Green's function. And so that's equivalent to solving this differential equation here. And so what you get here is a linear combination of Green's function, but that are shifted at those discontinuities at the location of the Dirac. And for example, here is my example of piecewise constant function here. So here the Green's function for the derivative is the Heaviside function. So if you do just a linear combination of Heaviside functions, that will give you the first term. Now, the tricky part is that is the non-empty null space. And that requires the specification of boundary condition. And to tell the truth, that's where 99% of the math are, okay, in getting the things right, is in dealing with the boundary conditions. But the rest looks pretty easy. And then actually there, now to make the connection, in fact also with Genoa, because I think Tommaso Poggio, Girosi, probably from here. And so there is actually a link with regularization theory, that if you now consider like a data fitting problem, like where you want to fit y's with no functions so that it matches some y's, or a regression problem. So now if you put a regularization that is some Hilbertian norm, squared norm in a reproducing kernel Hilbert space, so then you actually have a very nice solution which is given by this linear combination of kernels. And so what are those kernels? Now, if you have a reproducing kernel Hilbert space, I think you know, some specialists who know that much better than me just sitting here. But if you have a reproducing kernel Hilbert space, so there is a unique reproducing kernel. So that is this kernel here that goes from RD to R, cross RD to R. And so then actually the solution of that problem, you just need to take a linear combination of kernels that are sitting on the data points. and now this thing you can generalize quite a bit by replacing the quadratic loss by any convex loss. And in fact the solution still holds, and this supports the theory of support vector machine, kernel methods, variational splines, etc. So that has been a very classical theme in machine learning, very successful. But now what about splines? So splines is almost the same story, but there's one difficulty is this non-empty, non-trivial null space. And so it means that instead of having this Hilbertian norm that's acting on F here, we have this LF, so L being the operator that I told you about before. and so this will only be a semi-norm. And so then you can solve the same problem again. And now you find that, in fact, you get a solution that is very similar. It's just now, if you have the operator L, now you have the Green's function that goes with L, but actually not with L, because it's a quadratic problem. It will go with L star L. And then you can write the solution as a linear combination of shifted Green's function, but now it will be Green's function of the operator L star L plus a component that is in the null space. And so what you find here is that the solution, in fact, is a non-uniform L star L spline. Okay, so and with knots actually sitting on the data points. And for example, if you take L equal D2, then you find that this is actually a cubic spline, and that was actually where the name spline comes from, because in the old days, people were like using like sort of rods to draw curves, and if you bend the curve, the optimal configuration is the one that has minimum curvature, and that corresponds to this solution here. Okay, so that's the L2 theory, but I think lots of you have been involved in compressed sensing and sparsity, and myself as well. And so what you want is to move to L1 rather. But now the problem with L1, if you're in the discrete domain, so it's pretty obvious, but if you live in the continuum, like many of you here, actually it's not really the L1 norm exactly that you need. And you need something else that goes with Radon. And so the intuition here is that actually in finite dimension, the L1 norm you can take as a dual of the L infinite norm. So there's a little the same idea here for going in the continuum, but instead of using L infinite, you use a slightly smaller space, which is C0, which is the space of functions that are continuous, bounded, and decaying at infinity. And, and why is it this particular space? Because, in fact, this space you can construct it by actually equipping S, so the Schwarz space of test function, with L infinite norm and doing the completion of that. And that's the way you get this C0. And then actually those space of bounded Radon measure are just the dual of those C0. And so this is associated with the so-called total variation norm, but of measure theory. And it's a very nice space because it's a space that's a little larger than L1, which is very good. And now if you're in L1, in fact, the M norm or total variation norm is the same. Okay, so it's isometry, isometric embedding. But what's super important for me here in this talk is that the Dirac impulses are included in this M space. And in fact, more important, those Dirac impulses are the extreme points of the unit ball of this M space. And this brings us to our representative theorem for general total variation. So it's something we figured out some years ago. And it looks a little like your problem of machine learning, but it's a little more general because here we can have arbitrary linear functional acting on the function, not just point evaluations, but it can be any functional. And for example, MRI, so it could be like Fourier coefficients, etc. And so there's actually very light hypothesis. It's just that those measurement functionals, they need to be V star continuous on that space here of admissible functions. And then actually there you can get this representative theorem for generalized total variation. And it now will look familiar because it says now if you're trying to minimize this problem, you will get actually a linear combination of Green's function. So it looks like the classical thing that is in the null space. So it looks almost like the classical stuff, but there's a huge difference. Actually, the Green's function are not sitting on the data points. Actually, there are no data points here, okay? Because they are linear functions. And in fact, there are less of those kernel positions as their linear measurements. And now what the theorem says also is that the solution set is convex, so it's not necessarily unique. And now the interesting thing is that all the extreme points, so which are the points that I wrote in red here, that they are actually of that form. They are splines, all the extreme points. And so now then all the other points in the solution sets can just be convex combination of those extreme points. And now, again, like the representative theorem of Schölkopf, you can take arbitrary loss function here, and this still holds. So for us, it was really nice because it means that if we're doing imaging and applying such regularization, for example, doing MRI or X-ray tomography, we know that the solution is a spline. So it was, very, very nice because that's my main area of investigation. Now, how does that relate to, let's say, machine learning? Let's go to the very basic, because some people say machine learning is an interpolation problem. So let's try to interpolate those points. So how would you do? Now, if you're a classical person, you do that, okay? You connect the dots, and in fact, this is the reproducing kernel Hilbert space solution. Now, if you're a modern sparse person, can you guess what you will get? Okay, so you get this solution here, and that's much less obvious, okay, because you have only one knot. Of course, I made it up. Right? You have only one knot. It's not sitting on the data, and it's much sparser. And this now is really like the solution of this M norm applied to the second derivative. So I forgot to say that in that case, of course, you have to use the right regularizer. So here it was the derivative with the L2 norm, and here it was a second derivative with the M norm. And in both cases, you get linear splines, but rather different character. And now there are many other admissible spline operators. So you can take any derivative, you can take any ordinary differential operator that gives you exponential splines. You can take fractional splines, so where in the Fourier domain, you take just I or j omega to the power gamma. You can also have fractional Laplacian if you go in higher dimension that goes all the way back to Duchamp thin plate splines. And you can have elliptic differential operators like you encounter in the theory of Sobolev spaces that will also give you sort of Sobolev type splines, or which are like Bessel kernels. Now, this was my spline primer, but not, we want to talk about ReLU networks. So, yes. Yeah, so this has been obsessing me for at least 30 years. So I can tell you a lot about that. But maybe just a very simple reason. If you were, let's say, using Gaussian kernels, okay, and if here there was a huge gap, okay, so your estimator would probably go down in between, and now. If you have the non-empty null space, actually it means the polynomials live in the null space. So rather than putting holes, it will fill in straight lines, okay, which is actually much better. Okay, but I can give you at least 10 other. Yeah. Okay. Yeah. 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 But we have algorithms. For example, there's an algorithm where we can find this guy. Yeah. So it's just, it will come out of the result of the optimization. So for example, if you discretize it, it will do it automatically for you, but there's even a clean way where you can use the parametric representation and it will displace the knots so that they go at the right places. But yeah, I mean, it's not trivial, okay? It's harder, much harder. Okay, so let's move to neural networks. Okay, so now, in fact, you can use the theorem that I just showed you to study the limit behavior of univariate shallow ReLU networks. And so here's one of those shallow neural networks in one dimension. And so you have some first weights W for the first layer. And the second layer, there will be V weights. And we have ReLU basis functions. And so usually a way to set up neural networks, you put weight decay regularization, which would be a L2 norm on the coefficients here. Actually, by the way, this is not uniquely specified like that because you can, let's say, multiply V by 2 and divide W by 2. And so that's the reason why we need a regularizer then that will make it much more unique. So now if we apply the previous theorem with, again, the D2 regularization, in fact, the output of this theorem gives us something like this. Okay, so it's an affine term here plus a sum of ReLU, and that's actually completely equivalent to this. And in fact, the argument of the proof is relatively simple. It's almost like 2 lines, but the idea being that the V and W, if you can rescale them, and so you have then this gamma parameter that is a free parameter, and then you try to find the minimum regularizer, and then you will find that actually the optimal configuration is when absolute value of W is equal to absolute value of V, and then actually the product of the two is exactly the A here. And in fact, then what you also have, maybe I didn't emphasize so much, but the generalized TV was actually L1 norm of the coefficients that are sitting in front of the Green's function. And so that was figured out first by Savarez with L1 norm, but I must say his argument is not correct because he uses L1 norm, and in fact the problem doesn't have a minimizer if you look with L1 norm. So there's actually a sort of limit point, but it lives in capital M, not in L1. and pi Novak. And in fact, we also have like an algorithm that will really find the sparsest solution. So now, okay, so now comes the interesting part with the radon transform. See, I'm a medical imaging guy, so I'm using the radon transform almost every day to solve computer tomography problems. And so the radon transform, so how can you define it? It's a little like if you're going in some hyper-spherical coordinates, but what you need to define here is first you need to define the unit sphere in RD, and so you will have like vectors, unit vectors sitting on the unit sphere, and so every vector here you can then consider a hyperplane where actually that's perpendicular to that unit vector, and then you can also like move the position of this hyperplane with this offset parameter t0. And so then what is the radon transform of a function? So what we are just doing, we are just going to integrate the function over all possible hyperplanes that are indexed by those two things here, the psi, which gives you the direction of the normal, and the t0, which gives you the offset. And so then you get something that are all possible integrals indexed by this t and psi. And now there's a very famous algorithm, computer tomography, that allows you to invert the radon transform, and this is done by the so-called filtered back projection algorithm. And so the idea is you apply a filter followed by the adjoint of the radon transform, and you get back your solution. And so why is that interesting? And so this was uncovered by Greg Angie, Pai Novak, who kind of generalized the concept. Is that, again, now let's go back to this shallow neural network, but now in high dimensions. And again, let's put our weight decay regularization. Now it turns out that we can have the same functional optimization interpretation as before, but we have to replace the second derivative by this thing here. So what is this thing here? There's a Laplacian followed by a radon transform followed by the filtering operator of computer tomography. And then out of there comes this solution here, which is completely equivalent. So now this paper by Paris Novak for me was super impressive, but I was not completely convinced by the math, and because they were, I mean, they were very much inspired by our own work, but there were a few loose points that, you know, made me dive deeper in it. But now I'm convinced it's correct. Okay, the theorem is correct, but the math needs to be stated a little more carefully. Now, actually, there's also like independent other work that goes in the same direction. So there's first this interpretation of Francis Barque of infinite width neural networks. And so the idea here is, okay, you have an activation function, which is this sigma. And now if you put a continuum of neurons that are indexed by some measure mu here, so this will give you the equivalent of an infinite width neural network, and then you will use optimization theory by putting a total variation constraint on this measure, and to get this kind of solution here. But actually this is related to a problem in compressed sensing of Duval and Perret, because this infinite width neural network, oops, yeah, this thing is annoying. Maybe I'll just use my, okay. This equation here of the infinite neural network, actually you can interpret it as a convolution of the measure with the activation function, but this is only along the radial variable followed by a back projection. And then actually, then it, I mean, the problem here maps into a spike deconvolution problem that had been also investigated by Duval-Perret and other people. Now, there's also, now I come to the connection with the work done here in Genova, because there's actually a more general concept of reproducing kernel Banach space. And here the idea is again to have a space that's somehow indexed by a measure. And now in your work, you put something more general than just this activation function. So it's some kernel here, rho that depends on x, theta, and also like a weighting kernel here. So then if you define a proper Banach space that goes with that, it's a little like, I mean, the problem here is that this is not necessarily a one-to-one connection between this integral operator and the function and the mu. And so therefore you have somehow to factor out some null space. But if you do that, you get the Banach space. And now with this Banach space, you can rewrite the problem exactly in the usual form. So it's, let's say, data term plus regularization. And you find also that the solution now will be a sparse sum of those kernels here, which are called the rho x theta k. So the idea being that there are only a few theta k, which in the case of this kind of configuration will give you a neural network with few neurons. Okay, so this is, let's say, the connection with what exists. Now, then I mean, this forced me a little to revisit the Radon transform, and probably, yeah, many results are known for the Radon transform, and so that will be partly a review. So here's just a redefinition of the Radon transform. Now, what's important is the adjoint, which is the back projection operator, which is given here. And there's also this important thing is the Fourier slice theorem. So a way to compute the Radon transform, the easiest way you go compute the d-dimensional Fourier transform, and then if you just look along a ray that is given by, along this direction psi 0, and do an inverse 1D Fourier transform along those rays, you actually will exactly compute a one-dimensional slice of this Radon transform. Okay, so now, in some sense, what this Radon transform does, it goes from Euclidean domain into hyper-spherical domain. So what we can also define, we can define hyper-spherical test functions and distributions. And so they work like in Euclidean domain. And so the distribution are just a continuous linear function acting on the test functions. And if now those objects, the test function, no, the distribution are locally integrable functions, then it will just give you this kind of inner product here, or integral representation. And in the case d equal 2, you can parameterize everything by the angle theta, like you're just being in polar coordinate, and so this Radon-domain inner product is given by that. So I will from now on denote it with this subscript rad, just meaning we're doing inner products or duality products in the Radon domain. Now, then there's a very classical theory of the Radon transform on S. And now the very beautiful result is that actually the Radon is a continuous mapping from S into Euclidean space to S into hyperspherical space. And that it's invertible. And in fact, the inversion is just this filtered back projection. And now, okay, so it's invertible on the range of the Radon transform, but that's a very important space. And I will call it S-rad. And also, what is this filtering operator? So it's a filtering operator that only acts on the variable t, but that is called the ramp filter in tomography, but because in tomography usually we're in 2D, but in higher dimension it's like absolute value of omega, so being the radial Fourier variable to the power d minus 1. Now we have a characterization of the range, and I think the earliest is given by the Russian mathematician Gelfand. So it's actually, you don't I mean, when you start in S, you go to S in the hyper-spherical domain, but not all of S in the hyper-spherical domain. First of all, you only hit the even functions. That's normal because the Radon transform is even. But what's less trivial here is that actually you have moment conditions. And so that, and then you have a condition here that if you look at the moments but along the radial variable, t here, any kth moment here, that must be a homogeneous polynomial in psi. And so essentially what this tells you, the easiest case is just the mean value. I mean, for every orientation, the mean value should be the same. Okay, so the moment with 1. and this is also true for higher order moments, and that's not completely trivial. Now, you want to extend the Radon transform to tempered distribution. And so one does it the usual way by duality. So essentially, you start by doing, okay, take f is now L1 function, phi is a test function. And so we just write this duality product. And now we know that this guy is an identity. Okay, it's just a previous theorem. Then what we do, we move the black guys on the other side by duality. and so then this gives us a Radon transform here, and here the adjoint of the K filtering operator, but it's a self-adjoint operator, so it says itself. And now this is always true for any L1 function. And now for defining generalized Radon transform, we use that as a definition to define, for example, here is a filtered projection of any tempered distribution. So it is some element that I will call GTEL that just satisfied this duality relation. It's a little like if I was moving that onto the test function. Now, there's a problem here, or something to notice. Here what we have is not just phi, but we have the Radon transform of phi. And this is an element that actually lives in the range of the Radon transform, this space that I call S-Rad. And now actually there's a difficulty here, because if you look at those definitions here, I mean, they're not unique. In fact, you can always find an infinity of distributions that will satisfy those definitions here. And so there's not a unique definition of Radon transform of generalized function. Now, if you look at the back projection here is also just defined by duality. Now here it's much better because at least it's unique. But now it's not injective, okay? Because it means that actually there are many tempered distribution in the Radon domain that will actually project back on 0. And so that's, in fact, the difficulty here. So it happens then that actually the back projection operator has a huge null space. And in fact, the null space mathematically is just the annihilator of this space S-Rad. So it's a huge space. And so it means that my generalized filtered Radon transform, I mean, it is actually defines an equivalence class of functions. Now, the first thing we can say that the null space actually is closed, okay, because it's continuous operator. But it means now that this filtered Radon transform applied to distribution, it's defined on S-Rad prime, which is an abstract dual of S-Rad. But this guy is, in fact, a quotient space of all the distribution in hyper-spherical domain, quotient out by the null space of the Radon, the back projection operator. So that means actually that those guys are equivalence classes. So if I tell you, for example, you know, Dirac is, let's say, the Radon transform of some guy, okay, it means, okay, I can add any H to it that is in the null space of the back projection operator, and the relation will still be valid. And so this is, it's actually not very practical to work with. But at least you can do a very nice theory, and this is a classical theory. So now if you work with these abstract spaces, you have that you can do the Radon transform. Even if it's an equivalence class, it's invertible, and you get back your distribution. And in fact, the inverse is always the same thing. Okay, so if you have here the Radon filtered, then the inverse would just be the back projection operator. Okay, so this is, you know, maybe that's the contribution here of my talk, okay? Or maybe it's known, okay, but I didn't find it. I looked at many books on Radon transform. So there's a nice theory of distributions with the Radon transform. There's actually not so much theory about Banach space. And since we're dealing with representative theorem, we need Banach spaces. And so I was looking for a Banach space theory of the filtered Radon transform. And so now what you can do in hyper-spherical domain, and a little like the trick I was using to construct C0. Now if you have a norm that's well defined in this hyper-spherical domain, now you can actually construct Banach space by just the completion of those test functions with respect to this norm. But now what we know that if we have S here in Euclidean space, if we go to Radon, we hit this space S rad, and then it's completely reversible. So now the idea, instead of doing the completion over this whole space here, let's just take this space here, which is a space on which everything works well, and now just do the completion of that partial space here, which is the range of the Radon transform. And then we have this theorem here, this Radon compatible Banach isometry, and it's essentially given by this diagram here. So now this X rad was the completion of S rad with respect to the X norm. This gives me a space, and now this space here is isometrically isomorphic to some space Y that, you know, the domain here are the Euclidean domain, such that if I'm in Y, I apply the Radon transform I get here, and then I can go back. Okay, it's an isometry. And now the good thing, it also works with the dual. Okay, because this space X rad has a dual that I call X prim rad, and then in fact all those operators are also there, but in dual form, and they go the other way around, and that will define a space Y prime. And so now it's nice because we have spaces that are Banach spaces on which we can do filtered projection and go back by just doing back projection. And now in the special case of our interest, now we will choose X to be C0. So completion with respect to L infinite norm. Now in this case, the space of interest will be the C0 rad, which is now just the completion of this S rad with respect to the L infinite norm. And then the space of interest is actually the dual of that space, which I call M rad, which is the dual of C0 rad. And then we have exactly the same nice bijection invertibility. So we have then this diagram here, and that will be the important one for my purpose here. So if we're in M rad, and I call this the space of Radon compatible measures, so it's measures that I can I mean, if I'm this space of measures, if I do here the back projection, I'm now in Euclidean space, and now I'm in a space that, you know, if I apply the filtered Radon transform, I have this isometry here. And so this is essentially the tool that I need. Then what's interesting is to study a little this space M rad. And in fact here I didn't even need to exactly define this space just by using abstract arguments. What was important is to find actually the properties of evaluation functional, actually that you also use it in your work. And now in that particular space you find that the evaluation functional, first of all, is symmetric, that it's continuous, and now nice because actually with norm 1. Now the nice thing here is actually that this evaluation functional is in fact the filtered Radon transform of a Dirac ridge, okay, which will be extremely important for the argumentation. Then, even I don't know exactly the space M, what it is, MRAD. At least I can specify its extreme points, and actually the extreme points are just in fact those evaluation functionals. And now also, if I have now a distinct set of points where I want to evaluate, if I consider this linear combination here, the norm of that is actually the L1 norm of the coefficient. So in fact you have all the properties like if it was a Dirac. In fact, as if it was an even Dirac. And now maybe we want to look a little closer at it. So let's try to construct those guys. Okay, so which are those Radon compatible evaluation functionals? And so here what we start doing is doing an elliptical Gaussian distribution. So it would be very thin here and elongated in the other direction. And now if I make epsilon smaller, so it will get thinner like this, but it will elongate more in the other direction. So this thing you can actually compute is Radon transform, which is given by this expression. So with a sigma that depends on the orientation. Now, one important thing with this function, if I look at the integrals along t, they're always 1. Okay, they're always the same. Even if the guy becomes a elongated Gaussian. And then actually we can take those guys and have them converge to those evaluation functionals. And so here's an example. So here if I have an isotropic Gaussian, if I do the filtered Radon transform, I get this sinogram. Now if I take the epsilon getting smaller, I get this localization effect around those points here. And if I make the epsilon very small, actually this thing will converge like to the even version of a Dirac. Okay, so now this was the theoretical part. Let's get to the dessert, okay, which is the representer theorem. So representer theorem for machine learning, that's the one I already mentioned before, the one by Paris Novak. So here it's a little more general, so you can apply any loss function E, anything that is convex, proper, etc. Now you have your regularization operator, which is the same as before, Laplacian, followed by Radon and filtering operator. Then one needs to define a native space, and that's the hard part of the story, is properly defining the space M delta R. And in fact, this native space is isomorphic now to this space MRAD, which are the Radon compatible measures and the affine functions. Okay, so it's okay, psi here is just arbitrary, strictly increasing convex function. And so here you have the general representer theorem, and so it just says, okay, now it's a little more general than what Paillet and Novak had said, because Paillet and Novak said there exists a solution of that form. Okay, here we characterize all solutions. And we say that actually the extreme points of the solution sets are neural networks, are parameterized by neural networks. Okay, with a number of neurons that is smaller than the number of data points. And then there are parameters like the orientations and the weights to put to the neurons. I mean, they will be part of the optimization task, the training, and also the bias. And now the nice thing also that you have the regularization here is just the L1 norm of the coefficients in front. Okay, so how do we get this representer theorem? In fact, we have an abstract theorem in Asha that for sums of Banach spaces, and it's a direct application of that theorem, but there's one delicate point. We needed to prove that the sampling, the evaluation functionals are weak star continuous on the space. And this, you know, it's a little like when I tell you 99% of the effort. I mean, you have also dealt with that problem one way or the other. So this is the 99% of the effort that has to do with the boundary conditions. Okay, so that's the hard part, just proving that the hypotheses of the theorem are satisfied. But then you can just apply the theorem. And in fact, what you have here is just a sum it's like a dictionary that is composed on extreme points of the unit ball of the underlying semi-norm, okay? Which are those neural nets here. Okay, so now to give you an intuition. Don't know if you're interested, but me as an engineer, it's nice to have as abstract math. Actually, what's hiding behind there is just the fact that now this function here, that's absolute value ridge, is actually sort of the Green's function of this funny operator that we defined. So because there was Laplacian followed by Radon and followed by filtered. And now you may wonder, okay, absolute value is not ReLU, but for us Spline people, it's not a problem because, I mean, you just have this equation here that the ReLU is actually, you can express it as the absolute value plus a linear polynomial. So since you are spanning the linear polynomial, you can always go from absolute value to ReLU. That's not a problem. So now let's try to do the math here, because they're relatively elementary. So now let's put a ridge that is along the coordinates. Okay, so the absolute value is just along x1, and then it's multiplied by 1 in the other direction. So then actually we compute the d-dimensional Fourier transform. It's easy because the guy is separable. So you take the Fourier transform of x1, absolute value, that's 1 over omega 1 square. Okay, so that's the tricky part, but just distributional theory. And then the ones, okay, you all know they are like Diracs in Fourier, so 2 pi Diracs. Now you apply the Laplacian. Okay, so the Laplacian, you all know that the Laplacian, actually here I put minus Laplacian. So in Fourier domain, this is omega square. So I just multiply this Fourier transform by omega square, which I'm doing here. And now I use the properties of the Diracs, because now they are like, the Diracs are along the other coordinates, so they will just knock out the values of the omega square along those coordinates, but the Diracs will still survive, okay? And then, in fact, this omega square divided by omega 1, it will give you 1, okay? Because the other omegas will go to 0, and so that will give you 1 multiplied by the Diracs. And so here, trivially, you can do the inverse Fourier transform. So what you find there's a Dirac along x1, and it's 1 in all other dimensions. And now, using the shift and rotation property, actually, here you can show just that if you take such a ridge, absolute value ridge, that if you apply Laplacian to it, you just get a Dirac ridge. And then, Green's function property, you just apply this property that was in the theorem about the evaluation functionals. And by the way, this just follows from the definition by duality. It's a one-liner. Okay, it's a one-liner property. And so this means that actually if I apply the operator to this ridge or to the ReLU version of the ridge, I actually get the equivalent of a Dirac in this Radon domain. Okay, so that's the main point. Then you need to properly define the space. Okay, so you have this operator here. Now, the delicate point is defining the native space. And I said it was isomorphic to MRAD cross P1, which were the affine polynomials. Now, the tricky part is to finding the, the relation between MRAD and this M delta R. And it involves, in some sense, the inverse of delta R, but it is a pseudo-inverse. Okay, so, and now how you define the pseudo-inverse? So first of all, you need to specify the null space, and the null space of my operator here is just the affine functions. Now we then actually need to specify a projector in that null space, and so we need to find a dual basis of the polynomials of degree 1, which I will call P star, but there's a systematic way of constructing, and then the pseudo-inverse you get here. So it is inverse Radon. This is just the the first part of the theory that was inverting the Radon transform, but then this is for inverting the Laplacian, and then there is an inverse Laplace, but you have to be a little careful here because you are dividing by 0 at 0 in Fourier domain, and mathematics don't like that too much. So so then you have actually to correct here to factor out the linear polynomials. And at the end of the day, I think this is probably the most enlightening slide. At the end of the day, you can look at this pseudo-inverse operator, and in fact it is an integral operator that is acting on the measures, exactly like you have in your theory. Okay, but now the kernel of that operator is different. If you work out the math, you find that the kernel of the operator is this thing which is like the ridge, but then there's this correction here that is given by the projection into the null space. And now it's very interesting because now you see the kernel, I mean there's like the input guy is the measure, so it depends on t and psi. Now the kernel, now it has here those variables that go with the measure, and the x variable goes with the Euclidean domain. Okay, so now what we can do, we can fix t0 and psi 0 and look just the dependence along x. And now if we go along one ridge, what we find, actually they look like ReLUs. Okay, so that's just the positive guys, but in fact on 0 it is an absolute value, and if I do the negative, they're like reversed ReLUs, but it just comes out of this thing here. So now if I fix t, actually this guy is a polynomial. Fix t and psi. This is a polynomial in x. Okay, but that will somehow transform the absolute values in ReLUs, in one-sided ReLUs. Then you can go the other way around, and I think this is the amazing part for the theory. The other way around, so what you fix x and let's say psi, you just go along t, and now what you find, so here I just put this kernel being delta, but in practice it's a modified version of delta. Now what you find is actually the kernel is compactly supported and continuous, so it's part of C0. So the theory is completely stable, and we also have this remarkable bound here, because okay, so if you move out, this guy gets larger and larger, but it is always bounded by x, and so this really ensures that in fact this integral operator is completely stable and okay, which I would say the first time you see it's not obvious at all. Okay, and so this then gets me to the end of the story, so which I call the return of the spline. I mean, I've not been very original in my career because I'm just turning around in circles, like finding splines everywhere. So foundation of functional learning, we are doing here functional optimization in Banach spaces, which are enabled by representer theorem. Now, if we use Hilbert space, we're in the classical framework, everything is super. But now we like also to use Banach spaces, especially non-strictly convex Banach spaces, that they're the most interesting ones, but also the hardest one with respect to the theory. and they promote like sparse representation. So splines and machine learning, traditional kernel methods, actually the math are completely almost parallel to spline theory, and you could even argue that they were inspired by spline theory. But now, if we use now those Radon-domain regularization, in some sense, what the Radon-domain does, it sort of squeezes those multi-dimensional functions to bring them back in 1D, you know, because neural networks are upon 1D activation functions. But of course, there's a deep world around, and so then this is only valid for shallow neural networks, and then you need to think, you know, what's happening in deep neural networks. Now, the nice part of the story here is, and this is also something that was mentioned by Tommaso Poggio, like, and probably you too, yeah, that in fact deep neural networks, if you have ReLU activation, they are in fact hierarchical splines, and that they will in fact generate stuff that is piecewise linear and continuous. And then you can also, in fact, also learn those activation functions, and there's also some work that I call deep splines. Okay, so then I have to thank many people here who have helped me with the work. Also to thank the ERC, because they've been actually kind enough. I'm probably the last one in Switzerland to have gotten an ERC, so that will allow me to go on to go on exploring this, and here are some references on what I just presented. Okay, thank you very much. Yeah, so I can send you the paper. Now I've written the paper, it's not yet submitted, but in fact the hard part was also getting the sigmoids, but I have everything. And actually what's interesting, then the conditions that come out of the theory, they're compatible with the condition that have been described in the literature. For example, Baron give some conditions, and so yeah, so in fact it is but there are some technical issues to showing that it's weak star continuous. Okay. Otherwise, yeah, so everything is yeah yeah I mean, it's. I have the same impression because it looks a little convoluted, but for me, what was already important, like, is you know, having a clean version of the Radon transform that goes with Banach spaces, because the one that you find in books like with distribution, or even Lizorkin, that I guess you guys have been using a lot, was not really appropriate to that. So I would say, since this part is not so easy, so maybe once we have digested this part, maybe there's a shortcut. By the way, you know, one of the main authors of there's Paris and Novak. I've talked a lot with Novak, and he tells me exactly the same thing. He tells me, yeah, there needs to be a shortcut, and so he has been trying to find it, but yeah, maybe. I mean, at least here you have it, okay? So but it's maybe a little heavy, and sort of a little reverse engineering. But then I mean, once you collapse it to 1D, you get just the second derivative. And I mean, the thing, okay, so there's the Laplacian, but the Laplacian for spline people is natural. And then you have this filtering operator, but if you think mathematically, is a little like you know, change of coordinates. So it's not such a big deal, okay, if you do the math, but I mean, it's very natural because that's the sort of you know, change of coordinates when you go in polar coordinates. Yeah. Okay, I love your story because it's also in the paper that I will send you. Yeah. Thank you for the question. Okay, so you know, one of the most successful neural network is ResNet, and it precisely has that. You know, the short circuit that allows you like to do the identity. And now if you look at the math, actually, you can also like establish universality properties. And it is a little like with splines, okay? So because let's say reproducing kernel Hilbert space splines is exactly the same story. There you have universality properties, but from what do they come? They come from the fact that actually you have S, which is the space of test function that's included in your native space. And since S is dense in everything, okay, so then you have universality properties. Now, if you don't put the affine term, you don't have this inclusion. So then it means the guy is not universal. Now, okay, neural network guys, there are lots of paper on universality. Usually they put a bounded domain. And so if you have a bounded domain, somehow you don't care on the affine because you just move your ReLU out and you can create an affine term on the bounded domain. But if the domain is unbounded, you actually need this affine term. And remarkably, it's the most important one, you know, because most of the energy goes into this affine guy. And, you know, like pragmatically, I would say, yeah, that's, you know, sort of explains ResNet. So keep an affine path when you do learning.